Okay, so if there are no other questions, we can start the lecture today. I wanted to actually today discuss islands in doubly holographic settings. But before I do that, let me just remind you a little bit about what we talked about last time, and a little bit. I'll try and remind you. I'll just try and explain the generalization of the story that we described last time to eternal setups, and then we'll go on to talk about doubly holographic settings. So last time, we discussed how you take some CFT D-1, and you couple it to a bath, and this bath has a CFTD. And then, so you have some coupling, and then in this bath, you could make some interface I, and you could discuss a region R. And if you set up the CFT D-1 in an excited state to start with, it has to be the case, I mean, for a generic state, that the region R, if you compute the entanglement entropy of the region R, then you will see a page curve. And we discussed many times many subtleties about the factorization of the Hilbert space and so on in gravity. None of those are relevant here because in this bath there is no gravity, and this whole setup could just be in the table in front of me, where on one edge of the table I have some defect and some degrees of freedom. The rest of the table is the bath, and then I make an interface and I can ask about the entanglement of one part of the bath with the other part of the bath. So there's a precise sense in which you can describe a page curve. And what is more, in setups where the whole system, this entire system of a CFT D-1 coupled to CFT D has a holographic dual, you can compute the page curve using an island formula. And this is the way it should be understood. As we were discussing last time, the interpretation of this, I think one has to be careful with. Sometimes there are words where people say, we are collecting the Hawking radiation from the CFT D-1 into a CFT D, but that's not necessarily completely precise. The completely precise setup is the one which we have in front, and then we can add words to that in the holographic dual. But one has a precise computation which one is doing. Now, even this computation that I described for you last time, where I just basically described the story of how if the CFT D-1 itself has a holographic dual, which has a CFT D as a matter sector and gravity. So if you could expand this whole thing to being gravity plus a CFT D. And I tried to describe in words last time how you would expect how an island, the emergence of an island, would allow you to derive a page curve for the entanglement entropy of R. But in fact, whenever we consider these kinds of time-varying situations, we have to wave our hands a little bit. And so really, the most precise setups where computations can be performed are eternal setups. And so I first wanted to introduce the eternal setups and explain in words once again what the story of islands is for these eternal setups. And then I wanted to go on and discuss how you can compute islands or compute more precisely these page curves using doubly holographic techniques. So a more precise setup actually is to take the setup that we have, but take two copies of it. Okay, so here's a CFT D-1. And it is coupled to a bath. This bath has a CFTD, no gravity. And there's a coupling between these. But now we don't only think of this system, we think of another system where there is another CFT D-1, and it's coupled to its own bath. Okay, so these systems, let's call this system the left system, and let's call this system the right system. Okay, so the left and the right systems are entangled but not interacting. Entangled, but they're non-interacting. And that's possible, right? You can always have systems which are entangled but non-interacting. In fact, the canonical examples we give of EPR pairs are precisely of this kind, right? You have two systems which at some point in the past interacted, and therefore there was some entanglement between them, but now they're not interacting. So the left system interacts with itself and the right system interacts with itself. So the right CFTD minus 1 interacts with the right bath, and the left CFTD minus 1 interacts with the left bath. But the complete left system is not interacting in any way with the complete right system. In fact, you could prepare this whole setup in what's sometimes called a thermofield double state, which I don't remember if we discussed earlier in the course, but is this kind of a state. So I could write psi the joint state. The reason I write proportional here is because I need to normalize it with the partition function, which is some trivial normalization. But other than that, we have here a state where both the systems are in some temperature, at some inverse temperature beta. And this E here is an energy eigenstate of the combined system on the left. Okay, so remember, we have four systems here in a sense. There's a CFTD minus 1, a CFT on both sides, and a CFTD on both sides. And this E here is an energy eigenstate of the full system on the left. And this is also and this ER is an energy eigenstate of the full system on the right. And you can check that in this state, if you were to compute the density matrix of rho L or rho R, in both cases, it would be e to the minus beta h. Okay, so it would rho L would be e to the minus beta HL, and rho R would be e to the minus beta HR. So I guess they're not equal, but rho R is the same thing with HL replaced with HR. Okay, and that you can see just from the formula in front. If you trace out either the left part or the right part, you will get a density matrix, which is exactly the thermal density matrix, because you'll get e to the minus beta E and sum of EE. And so this thermofield double state, in fact, is often introduced as a purification of the thermal density matrix. Okay. Now, in this state, it's clear that if you just look at the left system, nothing is changing with time because you're just in a thermal state. And if you just look at the right system, nothing is changing in time because you're in a thermal state. And this whole system has a symmetry. So let me just take. This whole system has a symmetry, which is that it's symmetric. It's invariant. So it's invariant under unitary operations where you take time in the positive direction on the right and in the negative direction on the left. Okay. You can see this by thinking about the state. Let me just show you actually the state once again. Okay. And if you look at this state, you will see that this joint state is invariant under the action of e to the I HL minus HR. And the reason it's invariant is, HL gives you some phase and HR gives you exactly the opposite phase because you have e to the minus HR. And therefore, e to the I HL minus HRT leaves the entire state invariant. Okay. Nevertheless, you see that this is not invariant. So it's not invariant under the action of e to the I HL plus HRT, right? So if you take time to go forward on both sides, right now we'll say something in gravity, but right now these are just statements about non-gravitational systems. The system is not invariant under the action of e to the I HL plus HRT, and therefore it makes sense in this system to sometimes ask about joint correlators between some part of the left system and some part of the right system. And such correlators may have interesting behavior as you evolve them in time under e to the I HL plus HR. Right? Of course, if you just take correlators on one side, that's just the thermal density matrix. On the other side, that's just the thermal density matrix. But if you take like joint correlators, like you insert like OL here and OR here, then this 2-point function OL OR may have interesting behavior under this, right? or in general will have interesting behavior under this. This is what I said right now is true about correlators, but of course you could also ask a question about the entanglement entropy of parts of the bath. So in particular, you could take the system and you could say, not only do correlators vary, you could also ask, not this. You could also ask how, if you took this system, and let's say I said, I want to consider the region here, let's call this R, and I want to take the union of this region with some part of the right bath. Okay. So let's call this RR and RL. So now we could consider the entropy of SR R union SRL. Okay. And that is something that we could consider, and we could ask how this entropy, which is the union of the right, some part of the right path and some part of the left path, varies with time. Okay. And that's an interesting question to ask. So as I said, even though both of these systems look like they're in equilibrium, if you ask about joint observables between these two, since the entire state is not invariant under e to the I HL plus HR, these kinds of questions are interesting questions. Now, it may happen that if you do, and the paradox that we are going to encounter today is if we compute, if this entire system, as I described previously, has a holographic dual. Okay. So if the systems have a holographic dual, then and this is precisely of the kind we discussed, then a naive computation of SL of this quantity we've written may grow in a way that is unbounded with time. And that does not make sense because we could arrange for this CFT D-1 to have a finite number of degrees of freedom. And so, it does not make sense that you look at this entanglement entropy between some region and, you do some computation, and this computation, this grows in some way which is unbounded with time. Now, this is, so of course, if you were to just do the calculation correctly in the non-gravitational theory, you would find that, you do not have this unbounded growth. But the reason, this is related in some sense to the information paradox is that, the naive computation that you need to do is related to the growth of the size of the black hole interior, as we will describe. And the point is that this growth is cut off by the appearance of islets. And that's what gives you a page curve here. Okay? So the paradox in this setup is going to be that we are going to take this setup that we have in front of us on this slide, where you have a CFT D-1, which is coupled to a CFT, a non-gravitational bath. And then, the whole system will have a holographic dual, and we will use some holographic techniques to do this computation. And we will find that if you're not careful about how we do the computation, unless we include this contribution of islands, this S of RL union RR might just grow without bound, and that is a paradox. Okay? So let me just try and explain why this has to do with black holes and why this is related to the information paradox. And to do that, I have to draw now the bulk dual of this setup. So remember, we've been saying that the CFT D-1 always has a bulk dual. And the bulk dual here is as follows. Right? So what is the bulk dual just first to the two CFT D-1s entangled with each other? Okay. So if I just take like a CFT D-1 and a CFT D-1, and I put them together in a thermofield double state, then the bulk dual is believed to be an eternal black hole. Okay. So this is called an eternal black hole. We will study this a little bit more in the last part of the course when we discuss big black holes in EDS. But this is duality, which is well established and well understood. So if you just take some CFTD minus ones and the CFT is a holographic, then there is a bulk dual to them. And if you put these in a thermofield double state, then you get an eternal black hole in the bulk. There are many interesting aspects of this duality. As I pointed out, the boundary theory is entangled, but it's non-interacting. Whereas in the bulk, it looks like you have some connected bulk, and so you might have puzzles about that. And in fact, some of the puzzles that we encounter first were initially developed to point out that this eternal black hole story doesn't necessarily make sense because of this feature. But as we'll see, the resolution now is via this formation of islands. The bulk dual to just the two CFTD minus ones entangled with each other is the eternal black hole. But the setup that we have is where we have taken the CFTD minus ones and coupled them to non-gravitational paths. And so if you do that, then you get the following setup. You have an eternal black hole. Okay. And the eternal black hole is now coupled to some region which does not have gravity. Okay. So this is gravity plus CFTD. And this part here is no gravity and the same CFTD. So I hope it is clear how this drawing that I have is a bulk dual to this setup that I was drawing earlier, where you had a CFTD minus one, a CFTD minus one, coupled to a CFTD. So the CFTD is just carried over. It's just in one case, I drew a Penrose diagram. In the other case, I drew just some naive space-time diagram. So this is actually, this region is the same as this region. Okay. And it's this region, the CFTD minus one, that I have blown up. So it's this entangled state here in the middle that I have blown up in this way. Okay. So that is the dual of the system that I was describing previously. And now in this system, I said you wanted to compute the entropy of the union of some part of the system on the left and some part of the system on the right. And the way we do that is as follows. Let me just erase this part here. We take some Cauchy slice that runs through the system. And now I can compute in this Cauchy slice this is RL and this is RR. I can compute the entropy of, I'm sorry, the red is a little bright, but in any case, the red parts are RL and RR, and we can compute the entropy of RL union RR. And the reason a naive bulk computation gives you the wrong answer is because if you look at the slice that you have in front, and if you start pushing this slice up, like higher, right now I'm just saying some words, and then we'll do something more precise where I'll explain to you how it is precisely that you get some unbounded growth. But if you take some slice at a later time, then you see that the length of the slices in the interior tends to grow with time. Okay? And that's something that we will find and we will show. And so you see this, this is now RL at a later time, and here's RR. Okay. I hope you can see I have two slices. One is below, which is drawn the thin line. The other is above, which is in the thick line. And I've just evolved the slices with time on both sides. And the point I'm trying to, which I have not justified, but which I'm claiming, is that the unbounded, and we will justify later in the lecture, the unbounded growth of S of RL union RR has to do with the increasing or volume or area, the increasing volume of the interior. So, in the bulk, you have a black hole. And if you just look at this black hole and you draw these slices, you see that the thick slice looks like it has a larger volume in some sense than the thin slice. And we will compute that later in this lecture. And this wrong calculation that I said you need to do to get a paradox is that you take this dual as it stands, and if you're naive about how you compute the entropy of S of RL union RR, you will find an unbounded growth which has to do with the increasing volume of these slices. And the resolution to the growth is that, in fact, you need to also include the contribution of an island. And the island is something here. Okay. And when you include the contribution of the island, it purifies this RL union RR. And that purification cuts off the unbounded growth and gives you a page curve which flattens out after some time. Okay, so that's just some words about what we are going to expect. So just to say once more, if you just do a naive curve of this S of RL union RR with time, you get some growth. And if you were not careful about including the island, you would get the growth that would just keep going. And then, but at some point, when you do the correct computation in the bulk using islands, you will find that the growth gets cut off. Okay. So that's the story that I'm going to try and describe. And the paradox here is that this unbounded growth can be related to the fact that you have this growing size of the black hole interior, which would suggest or might suggest that the black hole interior has an unbounded number of degrees of freedom, and we know that's not the case because the entropy of the black hole is bounded. And so the fact that it gets cut off can be thought of as a version of the information paradox. And this is the version of the paradox that can be resolved most cleanly with islands, as we will now describe. So far, I've just tried to, wave my hands and say roughly what the story is. I'm now going to make all of this more precise in a doubly holographic setup. This story can also be made precise in a 1+1 dimensional setup, but that I think involves more technical details. The doubly holographic setups are simplest to understand. And so I thought I'll discuss those. But if there are any questions about this general story before I say something more precise, I can take them now.
Yeah, just a question about the boundary conditions. I probably missed it. But what kind of boundary conditions do you have?
Okay. So I'll assume that
Suvrat, there is a question. Actually.
There is a question. There is a question in the chat. No.
No. I think he's too hollow. He should speak up.
Oh, sorry. Can you understand me now? Or is it still soft?
Sorry, I can't.
Wait, sorry. Is it better now?
Yeah, now I can hear you.
Okay. Sorry about that. I'm using a new microphone.
Sure. Yeah.
I had questions about the boundary conditions. What kind of boundary conditions do you use? Because I thought for the eternal black hole, they would have to be reflecting, but now it seems that they are transparent in the sense that.
Correct. These are transparent boundary conditions. Correct. So we will make this more precise, and I'll give you an example where you can where I'll show this figure. You're right. You will need transparent boundary conditions in the bulk.
Okay.
So you'll have to take an entire Cauchy slice, and you'll have transparent boundary conditions, and then you take gravity on the Cauchy slice, and it's dynamical for some region and not dynamical for some other region. And you're absolutely right. You'll need transparent boundary conditions.
But even though the transparent boundary conditions, you're still in some sort of eternal black hole.
Yeah. So maybe I'll write down in a few minutes maybe a dual black hole, or maybe not a few minutes, maybe in 20 minutes, a dual black hole solution where you can see this being realized.
Okay. Thank you.
Okay. So okay, so actually those are good questions, and let me try and make this precise, because so far I just said some words. So the first step we're going to take, in fact, to making this precise is we will take. So we've been talking about the CFTD, but we're going to let's take the CFTD itself to be holographic. So far, this is not a condition that we impose. We said that we want to have this general CFTD, which is just some matter, and it's just a conformal field theory. But in fact, you can understand things most clearly when the CFTD itself is a holographic theory. Okay. Now, when this happens, we find that the systems for which I've been drawing two pictures, one a non-gravitational picture and one a picture with a dual, actually has three descriptions. So now we find a system which has three descriptions, and the three descriptions are as follows. Okay. One is the description which we had unchanged, right? Which of course remains valid whether or not the CFTD -1 has a holographic dual or not. which is a CFTD minus 1 coupled to a non-gravitating CFTD bath. So this description, of course, just remains unchanged because this description doesn't care about whether the CFTD is holographic or not holographic. It's just what it is. We have a second description, which is the description that also we've been talking about, which is a CFTD coupled to gravity in ADS. And further coupled to a non-gravitational bath. Okay, this is the system. This is the bulk description that we have been talking about so far. Okay, so we've talked about both of these descriptions so far, and they are just what they are because they don't care whether the CFTD is holographic or not. In fact, from now on, we are going to use description 2 mostly for words. And we'll think of a description 3, which is the following, which is a theory of gravity in ADS-D plus 1, okay, which is terminated by a brane. Okay. Now, why is this the right way to think of things? And you see, the way you should, it's kind of clear if you just take description 1 and think of the CFTD as being holographic, that you should expect a dual of the form of 3. And let me draw a picture, which might make it clearer. Here is the description of description 1 that I described, which is a CFTD. And here is my CFTD minus 1. I have suppressed many dimensions, and so the CFTD minus 1 just looks like a point. It's just living on some boundary of the CFTD. Now, if you just had the CFTD and it was not living on a half plane, it was just living everywhere, then we know there would be a bulk ADS dual, and you could think of this as living on the boundary of that bulk ADS dual, right? So if you just had the CFTD, then you would have said that, well, there's a bulk ADS dual, ADS-D plus 1 dual. Right? Now you have taken the boundary theory and you have terminated the boundary theory at some point with some defect or some boundary conditions. And it's natural to believe that you should also terminate the bulk with some boundary conditions. And that's what leads to the idea that you should terminate the bulk also with a brane. Okay? I have to say that these derivations are things which people have studied for a long time, but there's no top-down derivation of this. But it's a natural conjecture for what in some cases there is, but in many cases there isn't. But it's a natural conjecture for what you expect the dual of a CFTD coupled to a CFTD minus 1 to be. It is that you have this bulk ADS-D plus 1, and at some point it is terminated by a brane. Okay? And in fact, it's most convenient for us just to think of the duality between what we have here. This is description 1. And this, what we have in the bulk, is description 3. Okay. Now, you might wonder, where did description 2 go? In fact, if this brane is of the right kind and if the boundary conditions are of the right kind, then this brane has the property that, if you compute the modes of the graviton in this bulk ADS-D plus 1, there is some graviton wave function that is kind of localized to the brane. So this is these kinds of models that were studied extensively in phenomenology called Randall-Sundram models. And if you think of this graviton, if you take this system, the setup that you have, and you try and do a Kaluza-Klein reduction by trying to get rid of this additional D plus 1 dimension, then you can also find an effective description, roughly by straightening it out. So you have this brane, which is, which is gravity plus a CFTD, and that's coupled to a CFTD. So this is the description that you would get by taking the setup on top And then, by reducing the setup, by trying to get rid of the extra dimension, by doing a Kaluza-Klein reduction. And if you did that, that's like straightening out this boundary and just thinking of this boundary, but instead of the CFTD minus 1, thinking of the brane, which is the gravity plus the CFTD. And that's the description 2 that we've been discussing. But this description 2 is, in fact, the hardest to get control of. And therefore, what we will mostly discuss from now on is description 1 and description 3, and not this description 2. Although, if you want to think of where those words came from, this is what you should think of. Okay. So now this
Can
is
I quickly ask something about this?
Yeah, sure. Yeah.
Yeah. Can you understand as description 2 living on this brane? Is that how I should view it?
Yeah. So you can think of this description 2 as being, some localized matter which lives on the brane. And that's right. So it's exactly like a Randall-Sundram brane. There's some matter, there's some graviton, which is localized to the brane. And so, in these Randall-Sundram setups, this is what we were, we talked about there being some matter which is confined to a brane, and then there's some dynamical gravity. And the way the dynamical gravity is realized is that all of us actually live in a higher dimension, and there is a mode of that higher dimensional graviton that tends to get localized in the brane. And that's exactly what we're thinking of here.
Okay.
Right. So in this description 2, there's a CFTD which lives, right?
Okay. Yeah. Because should I understand, this is what I first thought, that this brane, you have to have this brane, the fact that this ADS D+1 space terminates at the brane, because otherwise you also include the degrees of freedom of the CFT D-1, and then you get a ADS D space that is dual to an ADS D+1 space, and that you don't want.
Yeah. When you talk about the brane, you don't also include the CFT D-1. So in this drawing that I have, there's some redundancy. So either you think of the bulk ADSD terminated with the brane, or you think of the CFT D-1 coupled to the CFTD. You shouldn't think of the brane and the CFT D-1 and together. Yeah, but the CFT D-1 encodes for the brane, so to say. The CFT D-1 encodes for the brane. Although, one of the subtleties we'll see is that when the CFT D-1 interacts with the CFTD, it might happen that some degrees of freedom on the brane are actually described by the CFTD. So indeed, naively, you would have thought that the CFT D-1 encodes entirely, in somehow the degrees of freedom here, like I erased. Somehow you might have thought that the degrees of freedom here encode for what's happening in the brane. But the whole point of the island proposal, or not the, which we'll see, it just arises from standard entanglement wedge reconstruction, is that it might sometimes happen that degrees of freedom here actually encode for degrees of freedom here.
Yeah, thank you very much.
Okay. Great. Okay.
Can I ask you a question?
Yeah, sure. Yeah.
Do you also consider a holographic dual for the CFTD that was in the gravity region?
Yeah, so that's how we got this. So this is the same CFTD that was in the gravity region. So it's this bulk ADS D+1 dual is the bulk ADS D+1 dual of the CFTD. So you see the whole setup, which was a CFTD +1, which is what we were drawing. We had a CFTD and a CFT, here. So this was description 2 here.
So it's so you're considering all the CFTDs on the entire slice, and then consider the holographic dual of the whole thing.
That's right. So you have but remember, this description is 1 dimension lower. So this is a CFTD, so it's a D-dimensional description. The description that we have here, and the description we have here is a D+1 dimensional dual of this D-dimensional.
Yeah, I understand. I thought that in your new description, that CFTD is only the one that was living in the bath, but you're saying it's the whole thing, including the the middle region.
So there are 3 descriptions. In one description, you have a CFTD coupled to gravity, coupled to a CFTD in the bath. So that's description 2.
Oh, sorry. Okay. So
this is description 2. And then there is a description 3 in which, there's no CFT inside. It's just gravity in ADS D+1 terminated by a brane. There's no CFT anywhere here. It's just, some theory of gravity, as we usually say, and maybe some string excitations and so on. And then there is a system, and there's a system where there's no gravity inside, which is where you have a CFTD -1 coupled to a CFTD. So there is this where there's no gravity, there is this where there's no CFT, and there is this hybrid description in the middle.
Okay, I got it. Thanks.
Great.
Yeah, I have a question about this third description.
Sure,
So
yeah.
if I look at the third description and try to see the Penrose diagram of it, so it is like a global ADS in which there is a brane sitting in between where the space-time ends abruptly.
Yeah, it's a brane sitting in between, but this brane actually reaches up to the boundary. So, one example that we'll do right now is where, you just have some transverse directions and this brane is just sitting at some constant value of the transverse directions. That's actually the simplest setup in which you can do this.
Okay.
This brane is, it's not, it's not sitting, it's sitting in the bulk, but it reaches all the way up to the boundary. So for instance, if this was like a transverse direction, then you could just cut off the transverse direction by a brane. And that's actually one setup where we understand what the description is. That's really an orbifold of the boundary theory.
Okay. And if you take a particular time slice in this Penrose diagram and try to look at the entanglement wedge of some region, then that wedge hits the brane also.
That's exactly what we're going to do now. So it's when when that wedge hits the brane that you get an island. And when when the wedge does not hit the brane, you don't have an island. So that's so islands are exactly this. Okay. So we're now going to take this. So by the way, what we have here is a constant time slice. Time is not running on the y-axis, right? And now you can compute like just minimal surfaces for different parts. And when those minimal surfaces reach the boundary, reach the brane, you'll have an island. And when they don't, you won't have an island.
Okay. Thanks.
Okay. Let me just say one thing. Sorry, is there a question here? Yeah.
Oh yeah, one more question about this construction.
Yeah.
Your answer to the previous question, and isn't it the right way to think about proposal 3? The fact that you have a CFTD ending on a defect, and that bulk dual is a dual to the CFTD ending on a defect in the bulk. So, in some sense, isn't it true what Batul was saying that dual is effectively the bulk dual to the CFTD living only in the bath and not to the CFT dual living in the gravity side in proposal 2?
Oh, you mean CFTD living only in the bath with dynamical gravity. So that is something which, so that would have a D-1 dimensional dual, right? Which is this, sorry. Is it not the dual to a CFTD only living in the bath? Yeah, so if you took the CFTD only living in the bath and you did not have, you see, at some point you're terminating the CFTD with some boundary conditions. And when you terminate it, you might need to add in some additional degrees of freedom. That is the reason you have this CFTD -1. You could take the CFTD and you terminate it in some way. And when you terminate it or you put some boundary conditions, you might need to add some additional degrees of freedom of that boundary. And that's why I said there's a CFTD -1. Maybe I didn't understand the question. Can you, your question was, why do you need the CFTD -1 at all, right?
No. My question was, this bulk dual in picture 3.
Yes.
Can't be seen as a dual of the CFT living on both the bath and the gravity, which is dual to CFTD -1. Like this bulk CFT dual, this bulk dual in picture 3 is the bulk dual to the CFTD in the bath, and then you have an end of the world brane due to the fact that you have the CFTD -1, right? Like you cannot see the bulk dual as a dual of the CFTD in the bath and the gravity system dual to CFTD -1.
Sorry, I didn't understand. Why can't you? You're saying the description 2. So there is a description where you have here. This is description 2, which you can. So there are 3 descriptions. Are you saying that description 2 does not make sense? Is that the question?
No. I'm saying description 3 is not does not imply that the bulk is a dual of the CFTD in the gravity side of description 2. It's just dual of the CFTD in the bath side coupled to CFTD -1.
Correct.
Is that right?
That is correct. Yes.
Okay.
Correct.
Thank you.
Okay, great. So now, as was already asked, what we want to do is exactly take this system and we want to compute in this setup, we want to compute minimal surfaces. Okay? So here is our CFTD. It's coupled to a CFTD -1. Here is our bulk. Oh, sorry, I should say one thing before that. Sorry, I forgot to say one thing. One thing you might ask is, what is it that controls the shape of the brane? When do I decide like what kind of brane I'm allowed to put and what kind of brane I'm not allowed to put? Okay. So in fact, as I said, we don't in most cases have like a complete understandings of what these branes are and how we understand them. But of course, if you were to just try and do effective field theory in the bulk, then for the brane, you would write down some action, which would just be, the induced metric on the brane with some tension. So this is the brane tension. And this comes from the induced metric. And this is the simplest kind of brane action you could write down. So if you're looking for brane world solutions and you try and write down a brane action, which is of this kind, just the induced metric and the tension just integrated on the brane, if you try and write down an action of this kind, then you find that, if you take a space-time and you try and put a brane in it, you need to ensure that certain boundary conditions are satisfied. And the boundary conditions that you need to satisfy are some version of the Israel junction conditions. So sometimes, you will see these papers where they work very hard to find a brane solution. And you might say, why can't I just take some black hole solution and just put a brane where I want? And you can't, because in general, you have to ensure that the extrinsic curvature of the brane satisfies this junction condition, and that's when you're allowed to terminate the space. So, in the bulk, the problem that you need to solve in the bulk is you need to find certain geometries where you can put branes. And there are two ways you can do this. Either you can look for geometries which are very nice and which have some nice symmetry. And then it's easy to put a brane. You can guess, where you can put a brane. Or you can say, well, I have some geometry, and then I want to work out, what the shape of the brane should be in the geometry so that it satisfies these junction conditions. And that is sometimes a much harder problem. But I just want to point out that, you might have this question of why it is you can't just put a brane in of arbitrary shape in an arbitrary geometry. And the main obstruction is the fact that you have to satisfy these junction conditions. The equation that I have written here is exactly a version of the Israel junction conditions, which some of you have probably studied. But it's precisely what happens when you take when you have shock waves or other such setups, and it's what you need to satisfy also to put in these branes. Okay, so from the bulk perspective, this is the main complication. But we will sidestep this complication by looking at a particularly simple setup where you can put branes just by symmetry, and you can put branes which have a very simple shape just by symmetry. There are other, there is a lot of work in the literature on trying to look at more complicated solutions and putting branes in more complicated solutions. And then sometimes you might need to solve this equation also numerically to find the right brane shape given a certain geometry. Okay, so that being said,
Okay, but yeah, I have a question.
Yeah,
about this. But the shape of the braid is also depends on some of the properties of the CFT, right?
So in the bulk, so now this is just an effective field theory description.
Okay.
So from some top-down perspective, that's a different thing, and we don't know how to derive that except in some extremely simple cases. So now in the bulk, I'm just taking an effective field theory perspective where I'm saying, let me take a brane and let me try and put a brane in ADS. And from this point of view, I'll just write down the leading term in the effective action. The leading term in the effective action is just this term that I wrote down is just a tension in the area of the brane. And if I write down that term in the effective action, then for the whole solution for this ADS D plus 1 to be a solution with this brane, I have to make sure that I satisfy some boundary conditions. So
okay,
this is not some deep prescription that's coming from saying, I wrote down the CFTD coupled to gravity, and that gave me some deep action or some precise action. But it's an effective field theory perspective of when you can find classical solutions with branes put inside ADS. Does that answer the question?
Yes, sir. Yeah.
Okay, great. Okay, so now we want to compute in this setup where we have these branes. The entanglement entropy, and the entanglement entropy we want to compute is of some region R. Okay? I will soon make this an eternal black hole. But for now, let me just think about one side and let me make some comments. So we have to compute the entanglement entropy of some region R. And now, what is it that we would have usually done? You see, in this setup, actually, we don't even need to worry about, I said that we had this one loop correction to the entanglement entropy. But here, there are very few degrees of freedom that we expect that are living in the bulk. If this boundary theory CFTD was n equal to 4 super Yang-Mills, then you would have some supergravity, type 2b supergravity in the bulk. And, the one loop corrections and so on are unimportant. And so all you would need to do is try and find some extremal area surfaces and then take the minimum of those extremal area surfaces. And usually what you would have done is you would have said, well, let me find a minimal surface that goes from one part of R to another part of R. So this is a minimal surface. I mean, maybe a minimal surface. We haven't solved an equation, but this is a possible minimal surface. And then we could have said, let's compute the area of this minimal surface, and that gives us the entropy of this region R. Okay? But in addition, so let me just write down some rules. Okay? We consider extremal surfaces in the bulk, which is what I just explained. But in addition, we are allowed to consider surfaces that terminate on the brane. Okay? So I'm also allowed to consider this kind of a surface. That's not nice surface. Let me make it nicer. So I'm also allowed to consider this kind of a surface, which terminates on the brane. And I'm also allowed to consider, so this is also a surface I'm allowed to consider. Okay, so this is an example of another minimal surface that's possible. And then I can compare the area. So this the second surface has two parts. It has part 1 and part 2. I have to add up the areas, and I can compare the area of the second surface with the first surface. Okay? So, but we are also allowed to consider, the main difference is we are also allowed to consider surfaces terminating on the brane. And we declare that the homology constraint is satisfied, and that's because the brane itself is in some region of dynamical gravity. And so we just, usually we would have said that, well, this doesn't satisfy the homology constraint, or if you looked at this, but we declare that because the brane itself is in the region of dynamical gravity, we are allowed to consider such surfaces. Okay? And these surfaces are the ones that are going to give us these islands, because you can see that, as we'll see a little bit later, sometimes these surfaces might be the ones that dominate. Okay. There's a second thing. Here there are some endpoints. So there's some endpoint P. When you do this, of course, when you minimize the surface, we also need to minimize over the endpoints P, or also need to extremize over P. So it's not that you fix some point. You're not allowed to demand a surface that starts at some point in the bulk or some point on the boundary and ends at some given point on the brane. But you also need to extremize over the end point P, okay, where P is this end point on the brane. Okay. So these are two rules. And as I said, the other rule is that for imposing the homology constraint, the brane is not counted. The homology constraint, remember, was that the region between the boundary region and the Ryutakinagi surface didn't have any other boundaries. And because the brane itself is in a region of dynamical gravity, it's not counted as a boundary. Okay? And when these surfaces become important, that is when you will find these islands. And this is an example of an island that you have in front. Okay? I should say that in all of this, there is no deep derivation. Okay, so there's no deep derivation, but this is a set of rules that are plausible and that work and give us interesting answers and are probably correct, but there's no complete derivation of where these rules come from and why we're allowed to make up, why we're allowed to use these rules. But these are the rules that are applicable and that have been used for computing islets. Okay. So now I'm going to do an example with a setup. Was there a question before that?
Very quick question. I just wanted to know if the section of brane between the two intersection points is included in the area term or not, or it's only the
no, that is not included in the term. So this is well, we'll see. So in all cases actually that we look at, we are not we will actually not even have a second section of the brane. But your question is, what if I had a setup of this kind? Should I include A over 4G from the part on the brane itself? Yeah. So in all setups, you're going to consider this is never going to arise, so the question is, do you need to actually complete this on the brane? I think the answer is that you should not include this section that lives on the brane. You should just consider these things. But I'm going to think about that a little bit more and get back to you tomorrow, because in all the examples that I worked out, actually, we are just going to have a single surface because this R is going to extend off to infinity, and so we are never going to include this section on the brane. But in principle, you're right. You could ask a question where you took a segment and you took these things, and I think the right answer is that you should just add up the area of this and of this. So you should just add up the area of A1 plus A2. And not include the area on the brane, but I will give you a more definitive answer tomorrow.
Okay, is that because the brane is considered as a bulk piece and not as a Ryota-Kayanagi surface?
Correct. So the brane itself is not something which you minimized over, right? The brane itself was just sitting there, and so you had this extremal area, and this extremal area just came from A1 and A2, and the shape of the brane was determined by setting some other boundary conditions, and so it's natural to not consider its area of A1 plus A2. But that being said, the point is that these rules are to some extent like phenomenological effective field theory rules, in that they're rules which work. So there is no like precise derivation of why it is that you should impose these rules. Why is it that you're allowed to relax the homology constraint? And so you may need to be careful about this in some settings, and that's what I wanted to check. But you're right that naively the most natural rule would be you just compute the area of these minimal surfaces, and not the area of this part in the brane.
Thank you very much.
Yeah.
Can
I
ask?
Yeah, sure. Yeah.
So I'm a bit confused by this setup, because in our earliest examples in the last few lectures, we were interested in the entanglement entropy of a part of a Cauchy slice, right? So at some fixed time, let's say.
Right.
Now here, this region R is taking an entire region of the boundary, so it's at different values of time, right?
It's still one value of time. I mean, isn't this is exactly the same setup that we had previously, where here. So let me forget about the bulk. Here is my region R.
Okay.
So let me take. So this is my region R. This is exactly what I had. If I now blow up the CFTD -1, it will become like something which has gravity. So you might have like dynamical gravity. But my region R is just what it is. So this is the same region R. You see, the part of the Cauchy slice we're talking about is now part of the boundary of this holographic setup.
Okay, so the R here that we are drawing, if I really believe this picture, would be at different values of time, right? It would be the entire the region R that you define by defining the interface, right? The entire region R on the right of the interface, not one slice of that.
Sorry, but I didn't realize. I was always drawing only spatial diagrams. I was not. You mean like these kinds of regions? There was no time in these diagrams, so maybe I should have been more careful about. So this was, it was not time running on the vertical. I was always talking about the entropy of like spatial subregions, because you always want to talk about the entropy of spatial subregions.
So when you draw the thing, for example, the CFT D-1 defect there, that's not that's at fixed value of time. It's not the boundary.
Yeah, I should have been a little bit. You're right. On the diagram on top, you have time running on the y-axis, and the diagram below, you do not have time running on the y-axis. I should have been a little bit more careful about those diagrams.
Oh, I see.
This is a fixed value of time.
Thank you.
In the diagram below. So here, this is like space.
Oh, I see. Thank you.
Okay, you're right that in these Penrose diagrams you had like so the CFT I was probably not very. You're right. I should have been more consistent in that. I should have drawn the CFT D-1 as a dot at all times, and not as maybe I should always have just drawn it as a dot and not as these lines.
It's fine. It's clear now.
Okay, great. Okay, great.
I have a question.
Yeah, sure. Yeah.
Okay, so for a given R region, I mean, depending on the values of tension, the brane could be anywhere. So is it? So how does this island?
The brane doesn't care about R. The brane R is the region which I defined or which we defined.
Yeah.
The brane is just sitting there in the geometry.
Yeah, but the formation of islands depends on the position of brane or the shape of the brane.
Correct, and depends on the position R as well. So for some regions R, you will get an island, and for other regions R, you will not get an island.
Okay, depending on the shape of the brane. Yeah, right.
Depending on the shape of the brane and of R.
Okay.
And of many other things. So depending on the shape of R and of the brane and other things in the geometry, whether there's a black hole or not, you may or may not get an island. So the rule is pretty simple, right? You just take this rule and you just apply the rule, and you see if you get some surfaces which end on the island, which end on the brane, or which don't.
Okay. Yeah. Thanks. Okay.
Okay, great. So let's do one example. Okay, just to show. I just want to show how this is a simple example. So let's take the following geometry. Okay, this is a black hole geometry. So let's take one geometry, which is just a planar ADS-D black hole. Where this I runs from 1 to some D-2. Okay, so this whole setup has D+1 directions, and I've picked out one of the planar directions, which I'm calling Y, which you see here. Okay, great. And h of z here is just 1 minus z to the power d by z0 to the power d. Okay. Now, in this geometry, one can put a brane at y equal to 0. In fact, this brane, this whole setup is just an orbifold of the boundary theory at y equal to 0. And so this brane, in fact, if you work out the conditions, doesn't even have any tension because there's no extrinsic curvature. But you can just imagine taking this geometry in the bulk and cutting it off at y equal to 0. Okay. So now in this geometry, we can compute these minimal surfaces, and this is a very simple setup where you can compute, and we will now explicitly compute these surfaces. Let me make a few comments about this geometry. So this geometry that you have, if you just think of the ZT plane, is the geometry of an eternal black hole. Okay, so if you just think of Z and T, it's the geometry of an eternal black hole. The horizon of the eternal black hole is should be 45 degrees. It's not 45 degrees in my line, but in my diagram, but this is the horizon. So this horizon is a planar horizon. So you can think of it as coming out of the slide and going into the slide. And I have cut it off at y equal to 0. Y is not displayed on this diagram. You can think of y equal to 0 as being the surface of the slide. And then the horizon extends for other values of y, which are positive values of y, which go into the slide. Okay, so that's how you should think of this diagram. And in this diagram, remember, you have t equal to, this is t equal to infinity in the coordinates that I had. This is t equals minus infinity. This is t equals minus infinity, and this is t equals infinity. Okay, so this is just the standard way in which you assign the coordinate time. And remember that inside here, t runs from infinity to minus infinity, and inside here it runs from minus infinity to infinity, and t becomes a spatial direction in the interior, whereas it's the time-like direction in the exterior. So this is just a standard Penrose diagram of an eternal black hole. Here is my right boundary, and here is the left boundary. Okay, great. So now, if you look at this geometry, there is clearly an isometry of the geometry, which is under t goes to t plus constant. Okay? But this t that we are talking about is the Schwarzschild t, which you can see on the left-hand side runs from minus infinity on top to infinity below. So if you were to really assign a t left on the boundary and a t right on the right boundary, then this isometry, which has to do with taking the bulk Schwarzschild t and taking the bulk Schwarzschild t to t plus constant, corresponds to taking tr to tr plus constant and tl to tl minus constant. Okay? So that's why I said that there's an isometry here which is under e to the hl minus hr tau. Okay? And that's because when you look at the bulk picture, t runs one way on one side and it runs the other way on the other side. But we are interested in asking questions, as I said at the beginning of this lecture, when you do evolution with e to the I hl plus hrt. Okay? So let me just explain what happens when you do evolution with e to the I hl plus hrt. Okay? So, and what we want to ask. So this was a slice of just the z and t coordinates. This is z equal to z0, of course. Okay? Let me now show you a slice at constant time. So this is a slice at constant time. This is my region R. Okay, this is my region R. And remember, I have two boundaries. So this is my, even though I'm drawing it on top, let me call this my left boundary. And then I have another region R, which is sitting below. And this is my right boundary. And here's my brane. So this is y equal to 0. Okay. This is y increases on this direction. And here I have z equal to z0, which is a horizon. And I have on opposite sides of the horizon, on the left side and on the right side, I have two regions. And I want to compute the entropy of the union of this RL union RR. Okay. So we want to compute the entropy of these segments. And we want to ask, how does the entropy of these segments vary as you push both segments forward in time? Okay. So we compute S of R, let me call this RL and RR. Okay. And we want to ask how this varies as we evolve both forward in time. And I emphasize that when I say forward in time, if I was to go back to the previous figure and RL was just a dot here and RL was just a dot this was RL and RR. And by forward in time, meaning I have to move both of them in this direction. Okay. So they both go up. So you see they both go up. And that is not an isometry of the geometry. The isometry is where this one goes up and this one goes down. And indeed, in this setup, if I was to make this one, evolve, if you think of time as now coming out of the board, if you were to think of, RL is going up in time and RR is going down in time, there would be no time dependence. But if you think of both RL and RR as going up in time, we will see interesting time dependence. Okay, and that is the situation where islands will be important. Okay, so now I'm going to actually compute for you how this holographic entropy works. And so the surface that we want to consider actually is a very simple surface. It's just a surface, because this RL goes off to infinity, we don't have to worry about its other boundary, and we just want to consider a surface that goes at y equal to constant. And this is a surface that, provided it moves correctly in the ZT plane, will give us, a minimal surface. Okay. Let me just tell you what we expect from this surface, and then we will derive it because it's pretty easy to derive. You see, what we expect from the surface is, let me redraw this diagram. This surface is going to go from one side of the boundary to the other side of the boundary. Okay. So it's going to go from RL to RR. And as I said at the beginning of this lecture, when it does this, it picks up a large contribution from this interior, which is the region that I've marked here. And this contribution tends to grow as you push RL and RR forward in time. Okay? And you can just see that, I mean, naively on the picture, but that's what we're going to find, that this contribution from this surface, which is drawn here, this surface that goes from one side to the other side, as you push RL, so, at this point, this is the surface at t equal to 0. And so it just goes to the bifurcation point. So this is the surface that there's one surface which just goes to the bifurcation point without exploring the interior at all. This surface that you see here is the surface that is drawn on this slide. But now you can start asking what happens as you evolve things, and you'll get a contribution from the interior, and that contribution will increase linearly with t. And that is what we are going to find. And that is what will give us the paradox that I described at the beginning of this lecture. So let me now do this derivation. So what is the action that we need to minimize, right? So the area that we need to minimize is just this. Okay, it's an integral. So I've written this curve. I've taken this curve that I had previously, and I parameterized it, or maybe the curve that you see on the slide, and I parameterized it as a function of z of t. Okay. Now it's actually not a curve. This is a minimal surface, but you see the surface just kind of extends infinitely in these xi directions, in these transverse directions. And so in some sense, we're actually computing an entropy density because there's infinite extent in the transverse directions. And the surface does not move in y at all. So it only moves in zt. And that is why, if you just write down the induced metric and you compute it, you will find this expression. But I want to emphasize that, this term that sits inside the square root might look like some geodesic length, but this is not a geodesic length. And you can see that from this 1 by z to the power d minus 1. This is what is telling you that this is actually a d minus 1 dimensional surface. It is not a geodesic. If the bulk was 3-dimensional, then this would be a geodesic. But in general, it is not a geodesic. It is a minimal surface. And the fact that it's a minimal surface comes from, you can see that because there's this additional term. And so this is not the same as just minimizing geodesic lengths from one side to the other. Minimizing areas involves minimizing a different action. And you see that here. Okay? So this is the action that we need to minimize. And now I'm going to explain how to minimize it. And we need to ensure that you go from t left on one side to t right on the other side. Those are the boundary conditions we have in this curve, as you see on the diagram. We fix that at z equal to 0 on one side, it ends up at some t left. At z equal to 0 on the other side, it ends up at some t right. For simplicity, we'll just take t left equal to t right. And we now need to compute what this area is. Are there any questions about this computation? I'm now just going to do some calculations. But if there are any questions about the setup or where I got this action from that I'm going to minimize, I can take them now. Okay, good, great. So you see, this action that we have here is independent of time. It's clearly just independent of time. And so you immediately get a first integral of motion. And the first integral of motion is just, if I call this whole thing L, it's just, del L by del Z dot minus L. This is a constant. And this arises because the action is independent of time. Action on the area is independent, is t independent. And because it's t independent, there's a first integral of motion, which is just z dot into del L by z dot minus L. And if you can compute what this is, you will find that there is, this tells you what z dot has to do. And what it has to do is that you'll find that this constant is h of z times z to the 1 minus d times square root of z dot squared by h of z minus h of z. Okay? So there's some expression that you will get, and you will find that this has to be a constant across the trajectory of the surface. So I might say curve, but remember this is actually a surface, but we are just looking at the zt curve, and for this function z of t, this has to be a constant for this function. But we have to be a little bit careful about the sign of z dot. So if you were to try and solve this equation to obtain z dot, you would need to be a little bit careful about the sign of z dot. And let me just explain how you fix that sign. You see, outside the horizon, you will find that outside the horizon, you will find that z increases for the trajectory, and that's because z is increasing away from the boundary, and t also increases. Okay, and therefore it is you can set for z outside the horizon, you can set z dot to be positive. Okay? Now, once you cross the horizon, then you expect that t will continue to increase, but on the other hand, z will start decreasing, because once you cross the horizon and you go deeper into the interior, then you expect that z dot will become negative, and that's just because you expect z will decrease. And so the correct way you fix the sign is you write z dot is h of z by c. I'm just solving this equation and putting the correct sign. H of z, what did I use for z0? Z0. Great. So this is for z larger than z0. Sorry, for z smaller than z0. This is outside the horizon, where you expect z dot is positive, and then you set z dot to be negative inside the horizon. It's the same expression, but just with a minus sign. Okay. So this has given us already the shape of the minimal surface. Okay, so this is it. Actually, in some sense, this is the answer. This is going to give us already one answer for the entropy. It's not yet going to give us islands, but it's we just need to now massage this answer and understand this answer a little bit better. But this is the answer for the shape of the minimal surface, and I'm now going to explain how you can use this answer and obtain one answer for the entropy. Great. If there are any questions, if any part of the calculation is not clear, please stop. Okay. Now, you see, what do we expect? Let's use a little bit more intuition to try and understand what this answer is going to be. I said something about what this surface does outside the horizon, but in fact, the surface also has a symmetry. It also has a symmetry because we've pushed t up symmetrically on both sides. And therefore, when you think of a surface that does something like this, the surface has a symmetry, and z dot goes to 0, of course, at the horizon. But think about what's happening also in the interior. You see, if you have a surface of this kind, then remember that t is varying in this way, right? What are lines of constant t? Lines of constant t as these are. This is how t changes, right? So t changes from being plus infinity, as I said, to being minus infinity here at this horizon. Okay. And so there is a part of the surface, which is this part in the middle, which is another part where z dot is going to go up to 0. Okay. So there's another part, which is where the surface will, if you just look at the surface, where you expect z dot to vanish. And indeed, let's call this point where in the interior, z dot goes to 0, and let's call that point zs. Let's call this point zs. What is ZS? It's obtained by taking the expression that we had for Z dot and just seeing where that expression vanishes. And ZS is the value of Z that solves this. And you see that this solution can only be in the interior because you have a C squared on the left-hand side and an H of Z on the right-hand side and minus H of Z on the right-hand side. And that only has a solution when H of Z is negative, which it is in the interior. Okay? So in the interior, at some point Z dot goes to 0, it goes to 0 at this point. And once you have this, you can now compute what the area is by just noting that the surface is expected to be symmetric about this point ZS. So you only need to do an integral on one side, and then you can just multiply that answer with 2. Okay? So you'll get an answer for the area, and the area, let me just write down what the answer is just this factor of 2 that I explained, and I'll explain what these terms are. I have to introduce, as we discussed also earlier, whenever you compute these areas, you have to introduce a UV regulator. And this epsilon that you see here is a UV regulator. And so this area I have cut off near Z equal to epsilon. And then I'm going to do an integral from Z equal to epsilon to this value ZS, which is the value that you have. And I'll do an integral of dz by Z dot. Let me just fix the sign by writing a mod. Okay. Oops. Minus H. I have to shift it. This is one way in which slides are better than blackboards. Okay. So this is an expression for the area. And the area always just counts positively. So, I put a mod sign for this, and I have regulated the area, and I'm doing an integral from Z equal to epsilon to Z equal to ZS of this area. Okay. So this is my formula for the area. What about the formula for the time difference? Right? And in the end, I said that I wanted the time to go from some TL here to some TR here, and I have to also compute, how much the surface travels in time. That also I can compute just by computing how much the surface has traveled in time till here. Okay? And so I will find that the amount that the surface has traveled in time is also given by, I have to be a little bit careful about this because, Z dot changes sign. And so I have to be careful about the fact that, time increases first. But then when I'm in the interior, I'm going from t equal to infinity to t equal to 0. And so I have to be a little bit careful about, what is the final value of time that I end up with. And so I have to be a little careful about, regulating this near the horizon. But provided I'm careful and I take a principal value prescription. In fact, time is going to go off to infinity near the horizon, then it's going to come back down from infinity. And so I have to be careful about, what is the value that it ends up at. And I have to be careful about canceling off the infinity near the horizon. And that's the reason I introduced this Z0 minus delta, this regulator here. But this is really just a principal value prescription. Okay. The other divergence that I had for the area is really a UV divergence that I had. It's something physical. Here, it's just the fact that, T was really not such a great coordinate system to choose. And it's a coordinate system that has the property that it diverges in the middle. And so to ensure that, I end up at a finite value of time, I have to be careful about taking the principal value when I integrate across the horizon. Okay. So this is the formula we have now for the area and for the time. Okay. So now we need to understand this formula a little bit better, and we will see already the expressions that we have. Okay. Let me now, I have only a few minutes. Okay, let me not try and rush through this. Let me just try and explain qualitatively, and then we'll complete the calculation tomorrow. If you look at this, you will see that there are. Look at the expression for the area. Okay? When you look at the expression for the area, you will see that there are various places where you might expect a divergence to come from. Okay? And the place you might expect a divergence to come from is when z dot vanishes. Okay? So remember, z dot vanishes near the horizon and near z equal to zs. Okay. Now, in fact, neither of those contributions gives you a divergence in the final area for the following reason. You can see that when z vanishes near z equal to zs, that happens here. And in fact, z dot vanishes like the square root of z equal to zs, which maybe you can see from this formula. Okay? If you look at this formula, you will see that there's some point where z dot goes to 0, but the way it goes to 0 is like square root of z minus zs when the term in the square root becomes 0. And so you can see that actually does not give you in general a divergent integral. And in fact, the horizon is not a problem at all because h is also vanishing at the horizon. But what you might be concerned about is the contribution that's coming from the area which is near z equal to zs. And that in general is not a problem. So usually z dot goes to 0 as z minus zs near z equal to zs. And that leads to a finite contribution to the area. Except if this value c is very special, if zs is at the point which maximizes this term here. So if zs is at a special value, which depends on this value of this constant c, which is some constant that characterizes the curve, if zs has a special value so that this term is actually maximized, then this first derivative z minus zs vanishes, and you will get a contribution which will here become 1 by z minus zs. And that will allow the area to become arbitrarily large. When the area becomes large, we find that the time also becomes large. And so by picking the value of c appropriately, we can make both the area and the time grow large. And that is what gives us this unbounded contribution to the entropy. Okay, we'll find some contribution to the entropy which grows linearly with time, which we won't do today, but we'll do tomorrow. And then we will also see how you can find a different surface which cuts off this growth of the entropy, which is the island surface, which does not move in time at all, but which rather moves as a function of y of z. And this island surface will cut off the growth and will give us the page curve. So I actually see that we are out of time, so I don't want to rush through this last part of the calculation. It's pretty simple and it's useful to do because this calculation has actually appeared in many times in the literature. And so it's useful to understand well. And so I won't rush through it, but we'll complete the calculation next time. So let me actually stop the lecture here. And then if there are questions, we can take them and we'll complete the calculation tomorrow.
Yeah, I got a question because we're now looking at the entanglement entropy of a union of our left and our right.
Right.
But from this, maybe we get to this tomorrow. But from this qualitative picture, should we? I mean, if we just look at the entanglement entropy of our right, shouldn't we get the answer we discussed last week? So when we not do the union, but
of just r right?
Yeah.
So that would not vary with time at all. There's no time that it would vary with. That would just be some constant which you could compute once and for all. So the whole reason you're getting a time dependence is because you see, if you just look at one part or one side, that side is just static. It's in some thermal density matrix, and so there is no time to anchor things to. If you just have r, if you just look at r right is some region on the boundary, and things are. If you just look at one boundary, things are time translationally invariant. So things are not time translationally invariant only if you look at one boundary and look at correlators between one boundary and the other boundary. So if you were to just look at r right, that would not have anything. There would be no time dependence, so interesting time dependence in that. And similarly for r left, it's only for s of r left union r right that you'll get interesting time dependence.
Yeah, because of this I think it's called the Hartmann-Maldacena surface.
Correct. So this surface was initially analyzed by Hartmann-Maldacena and correct, and so that's right, because of this surface. Exactly.
Yeah. Yeah, so in the case of one side, you always have the minimal surface, which is outside the black hole. Yeah,
Exactly.
Okay.
That's right.
Thank you.
I had a somewhat related question because
Yeah.
I'm still a bit confused by the general setup
Yeah.
we use.
Sure.
Because I don't have very straight what question we're really asking, because we're looking at the entanglement entropy of this region R union region left,
Right.
but naively in the eternal black hole case, if you take the whole boundary, it's in a maximally entangled state because both are in a thermofield double state.
If you take the
But
whole
now-
boundary, yes, the whole boundary would have RL
Yeah.
and RR just being, if you took everything, including the defect, you just get 0. Like if you took
okay,
everything,
exactly. Yeah. And if you take one boundary, you get a maximally entangled state.
correct. If you take one boundary, you would get the horizon area. If you took this boundary, you'd get the horizon area. If you took the union of the full boundary on both sides, you just get 0.
But what is it that gives the dynamics, so to say? Why does the entropy rise over time naively? Is there an evaporation going on, or what is the dynamics that makes
sometimes people say that, but that there's evaporation going on. But I think that it's the fact that the thermofield double state, which is this state, so let's try. If you look at this thermofield double state, it is a state which is where the phases have set themselves up in a particular way, where the phases are such that they are one for all of these energy eigenstates. And so the thermofield double state you should think of as a state where there are some very specific correlations that you have between the left and the right theories, because the phases are one. And if you go away from that, in some sense, there is exchange of information between this defect here, or this part of the boundary here, and this other part of the boundary here. And so at a different time, once you do time evolution, it's not so. In the thermofield double state, when the phases are exactly one, it so happens that this CFTD is kind of as entangled as it can be with its partner on the other side. So if you were to look for like the partner operators for operators that live here, they're right here. Okay. But as you start pushing both these in time, that's no longer the case, and now the partner operators that are most entangled with something here are not exactly here. Some of them might be here as well. Or you could say the other way around. You could look at the partners of operators here, and some of these operators might actually be living here at later times, whereas they're living, right here at this time. Does that answer the question? Let me say it in terms of correlators.
Yeah, I think.
Maybe that'll help.
Yeah, no, I think it's clear. So there are certain sense in which the degrees of freedom from the CFTD -1 they go to the CFTD, and then.
Right. Right.
Is that right? Yeah.
Yeah, that's one way of saying it.
And then the question you.
Yeah, go on. Yeah.
Okay. Yeah. So and then the question you're asking is, you want to calculate this entropy, but you calculate it holographically. So at some point you get an area contribution.
Right.
And kind of interpret the fact that as soon as you get this island contribution, that you have enough degrees of freedom in this region L union region R, that you can in fact get some holographic information and decode parts of the interior. So it's in a certain sense, it tells you how many degrees of freedom you need of the original system to reconstruct parts of the system.
Yeah. Yeah, you could say that way. It tells you how much. Yeah, I mean, of course, the number of degrees of freedom in RL and RR don't change. It's the entanglement that changes. But yeah, you could say it in that way. That there's some exchange of information between what was originally here and which now moves here, and eventually, enough information moves that you can reconstruct what's happening somewhere in the middle, somewhere here in terms of degrees of freedom that live here and here. So indeed, that's right.
But is it correct to say that if the island comes, that this is sort of a sudden phase transition?
Yeah.
And if the island comes, then suddenly you have enough entanglement to access this this
right
position.
But this is not something which is so unusual, and that's why we spent some time discussing the setups in flat space. Remember, even in empty space, even in empty space we had this. So in fact, this transition that is happening is I can just draw it in this place, is very similar to the transition that we saw happening in empty ADS, right? At some point we said, you took these unions, you took like something here, something here. I mean, so there's nothing, I mean, okay, it's different, it's a different geometry. And once you made these regions like big enough, at some point you suddenly transition to a different entanglement wedge. So earlier there was this entanglement wedge, and at some point you suddenly made a transition. So in this setup, of course, there's no time evolution of this kind. It's too simple for that. But we do see in other situations that as you change some parameters, you have a phase transition in entanglement wedges. So entanglement wedges do undergo phase transitions, and that's why here the phase transition in empty ADS was as a function of size. Here the phase transition is as a function of time, but in fact it's not only as a function of time. If you were to draw the entire phase diagram of whether this surface dominates or of whether this surface dominates, you would find the phase diagram would depend on this point y0 and also on time. So you would get a phase diagram as a function of two variables, y0 and time, and one of the surfaces would win for some values of the parameters, and another surface would win for other values of the parameters. And the fact that which phase wins depends on parameters is something you see also in empty ADS.
Okay, yeah, thank you.
Are there any other questions? Okay, the brane third description is hidden behind the horizon. There's a question in the chat. Yeah, the brane does go behind the horizon, but the brane is also the brane is also reaching the boundary. So because the brane is reaching the boundary, there is the brane is going to go all the way outside. So I mean, it's important that these branes reach all the way to the boundary. And so there is the possibility of an island. It may be that there is no island, but these branes that we have drawn here are never entirely hidden away from the boundary. They touch the boundary. So they're never entirely behind the horizon. Does that answer the question, Behrad, if you're still there?
Yes, thank you.
Okay, great.
I have a question about this dual picture.
Sure.
So we know that it has to be a black hole because of the original idea that the dual to a thermofield double is a black hole. Is that right?
In this setup, we wrote down a metric explicitly, which was a black hole metric. In this picture.
Yeah, but I'm asking why you wrote down this. I mean, how did you know that it should be this?
Yeah, good. Yeah, you're right. So in the earlier, so you maybe another question could, once you write down this metric, you could ask what is the boundary dual to that. But it's also true that we know that if you take the thermofield double state and if you're above a certain temperature in global ADS, that the dual to that is an eternal black hole. So you're right, that's something that we know from ADS CFT. If you're about that is the fact that you have to be above a certain temperature is relevant if you're in global ADS. Here we're in planar ADS, so even that's not relevant. But if you're in global ADS, you would need to be above some temperature, and you would see this eternal black hole in the bulk.
Yeah. So even though we are considering only a sub-region of the boundary, and we know that the state of the union of R and L is not a thermofield double, but nevertheless we are taking the bulk dual to be this black hole.
Sorry, this whole region is a thermofield. You see, if you take the entire boundary and
so
the entire boundary, it is a thermofield double.
Right. Yeah, but okay, I see.
So you see, you never ask about the dual to this region. I mean, you can ask about that in entanglement wedge reconstruction, but when you write down the full geometry, you take the entire left boundary and the entire right boundary, and that is in a thermofield double state. So this is, so in fact, what we have drawn here is really just an orbifold. So you could just take a standard thermofield double and just orbifold it. And, so it's the whole thing is in a thermofield double state. Now we are asking, in this thermofield double, we internally divide the degrees of freedom on the boundary into RL and its complement. So like this one and this one and this one and this one. And then, we can ask for the entropy of RL union RR. So once again, the question we are asking is a non-gravitational question. It's a question that's well defined on the boundary. And then we are answering it using this holographic computation in the bulk.
Yeah, okay. But another question about the brane, maybe I missed that, but does that play any role in your calculations?
So far, it has not played any role because we've just been considering this surface. But it will play a role because we will find that the size of the surface will keep increasing with time. And that is a puzzle. So, when people say we address the information paradox in the setup, this is the paradox that is addressed. It is the fact that if you look at this surface that is now on the slide, which I've highlighted, that surface tends to grow with time. And the fact that it's growing in an unbounded way with time is a puzzle. And you will find that after some time, in fact, there's another surface that wins because the extremal surface prescription tells us to minimize over extremal surfaces, and that surface will be this one. So, if you look at, so you'll find that after some time, this surface that's in the middle is going to lose to these surfaces, and these surfaces exist because there's a brane, and these are the island surfaces. So so far it has not played a role in the calculation, but it will tomorrow.
And another question is about this. I mean, in what sense it's a doubly holographic setup? It's just one holographic setup. Why is it doubly?
This is just one holographic setup. But if you were to look at this description too, there is another description of this, which is
okay.
So right. Then it's doubly holographic in that sense. So as we have shown it here, it's just a single holographic setup. You're right. So it's and this is actually the cleanest way I think that we understand islands. It's in this in the setup where you take a CFTD, you take a bulk, you put some boundary conditions, you have a bulk dual, and you're just computing standard minimal surfaces. But there's this description too where you say you have this is actually a CFTD coupled to a theory of gravity with CFTD, and then there are transparent boundary conditions, and then you can ask that. By the way, in this setup, in these brane setups, you can make this notion of transparent boundary conditions also straightforward, because that's just a question of classical solutions, right? If you have classical solutions, you hit the brane. Here you can set things up so that the classical solution just propagates from here to here.
Okay.
Yeah.
Thank you very much.
Sure. Yeah.
Excuse me, I have a follow-up question about this.
Yeah, sure. Yeah.
Maybe we'll see it tomorrow, but the idea of why you get an island, including the interior of the black hole in the let's say black hole living on the brane, then is the idea that those Ryota-Guyanagi surfaces, these extremal surfaces, end on a piece which is outside the horizon of the black hole, and the entanglement wedge you have to compute the entropy of includes the interval on the brane, which includes the interior of the black hole?
Yeah. So you see, if you look at these yellow surfaces that I've drawn, and you ask what is the entanglement wedge, it's the whole thing, right? Because so it's the entanglement wedge is everything, and this includes also the interior. I mean, here on this picture you can't see the interior, but it would include in the interior as well.
Okay, so basically the endpoints are outside the horizon of the black hole on the two sides, and so that includes all the interior of the black hole.
Right. So if you were to draw it in this picture, it might be clearer. If you look at the entanglement wedge, it'll be, let me draw it here. It'll be like this red region that I drew. So that'll be, that will be part of the entanglement wedge of this region, RL and RR. It'll include like some part of that region. That's why it'll include the interior.
Okay, thank you.
Okay. Other questions more?
Sorry,
yeah, sure, yeah.
Well, I had not even one more question, the same question, because I started thinking about it again, and I don't think I understand it still. So in what sense are we moving away from this thermofield double state? I still don't really see, because we take a subregion of this. So we take this subregion RL and RR.
Right. And then we push them up in time.
How do we transfer the entanglement?
No, we just push them up in time. We're not actually if you just think of the boundary, these regions are just moving up in time. So let me see, how do I draw the picture? So let's take some snapshots in time. So we have like a boundary which is a planar boundary. It ends at y equal to 0. So I'm just drawing some. So at some point this is like RL. So this is like what I was calling t equal to 0. So this was RL at some point. And then after some time, I just, I move RL up in time. So this is RL. And I just move RL up in time, but I have to also move RR up in time. So this is one boundary. I have another boundary, which is also at y equal to 0. And here is my RR. And I can ask, this thermofield double state was prepared so that at t equal to 0, what I was calling t equal to 0, was like a special state. There was like some special correlations between RL and RR at t equal to 0. At t equal to tau, those correlations have changed. And that's why I will find a different answer for the entanglement entropy of RL union RR.
But I don't really see why the
Sorry,
entanglement should
now
change.
I made it very confusing because I drew y equal to 0 and I also drew time on top. Sorry, I should have drawn a snapshot. Yeah. Why will the entanglement change? You see,
Because
maybe
there's no interaction between the sides, right? I mean,
let's think
between
of
RL
correlation
and RL.
functions. Maybe it's simpler to think of correlation functions, right? So let's say I take like OL. I take like a correlator at this point. Right? You can ask what is the operator on the right hand, or this is OR. What is the operator on the right hand side that's most entangled with it? The way you find this operator is, so if this is like OR of t, the operator that's most entangled with it is like OL of minus t. So like entanglement naturally goes in this way. And so if you were to ask like what is the correlator OR of t, OL of t, it would tend to decay with time. So the correlator OR of t, OL of t, where you make t positive on both sides, it would tend to decay with time. So let's think of entanglement in terms of Bell correlators. So in terms of Bell correlators, we are trying to ask, you have some operators here, and then you have some operators on the other side, and how much entanglement do you have? And so if you just take operators which live at the same point, of course, if you take the full boundary, you can always find some operators on the other boundary which are entangled. But let's say you just take operators that live at some point, and you at some point in the sphere. At minus t, you know where are the operators that have high correlators with the first operator. But if you start increasing both with t, you will find that this correlation function decreases with with time. It decays with time. It decays with time because OR of t does not have good correlators with OL of t. And that's in some sense what's happening here. There are some correlations between operators in RL and RR at t equal to 0. But at t equal to tau, those correlations may be different. So correlations do change between operators at one point between t equals 0 and t equals tau. And that's why the entanglement also changes. And maybe correlators is simplest to think of. If you can persuade yourself that correlators change, it will be clear that entanglement also changes.
Yeah, that helps. So, and the correlators change because of the information scrambles on the boundary. There will be dynamics on the left boundary, and the correlations will change because of that.
Yeah, it's clear, right, from the fact that if you evolve both in time, it's just not true that if you take the state EE, that this state is invariant under time evolution both on the left and the right. So this state has a symmetry, but that's only if you evolve time forward on the left and backward and right. If you evolve time forward on both sides, it's clear there's no symmetry. And so if you try to compute a correlator of this kind, you have to evolve time forward on both sides, and that's just not a symmetry of the state.
Yeah, thank you. That's clear now. Thank you.